Yeah, we already heard, I mean, from Terry, I think we are in living exciting times. Artificial intelligence is all around us, and I would like to take you on a journey how mathematics, modern mathematics, can actually contribute to it in various ways, in particular to make artificial intelligence reliable. As said, I mean, AI has a tremendous impact on basically all our aspects of our lives, and it will increase, I think, even more in the future. I mean, self-driving cars, robotics, also telecommunications, speech recognition systems. And I think lately, I mean, everybody is talking about ChatGPT 4, and which impacts that has. And even more sensitive areas, also in the legal system. I mean, many countries already introduced AI-based approaches, also, for instance, in the job sector. So, for instance, for pre-screening job applications. And then certainly also the entire field of sciences is impacted: medicine, biology, astronomy, also think of digital humanities, and so on and so on. I think it will lead to a paradigm change in basically every aspect of public life, society, which we can imagine. And so you see here on in the Times, the future is artificial intelligence. And I was also asked, I mean, there were several waves at some point of AI, but I think now AI has come to stay. And I think it's an exciting time we live in particular for mathematics, and this is what I would like to also show you. Now, in mathematics, what we observe is that already early on, we see in some areas a paradigm change. For instance, in the area of imaging sciences inverse problems that started early on, 2012. And you see here a list of classical problems people work on in this field. And what you saw that after 1 or 2 years, after these deep neural networks came up in particular, already 80% of the presentations at conferences used these new methods. They're extremely powerful. Why? Well, because here, I mean, we don't have a rigorous model what an image is. So that makes learning type methods so effective. That's another area I would like to just briefly mention, which is the area of numerical analysis of partial differential equations. A very well explored area, many exciting results. And you see, I mean, this area embraced AI much later, 2017. Why? Well, because, I mean, a PDE is a rigorous physical model. I mean, what is there to learn? But what turned out is that in the high dimensional regime, AI, in particular deep neural networks, can, to a certain extent, circumvent the curse of dimensionality, which otherwise is a huge computational problem. And so when that was detected, from then on, research basically took off. And now you see that also this whole area, basically, even find element methods and so on, is really swept by these new type of approaches. That all looks very exciting. But then, I mean, on the other side, so there was an interesting incident just a couple of years ago where at one of the big AI conferences, one researcher who won actually an award gave a plenary speech. And in his speech, he said AI, and so machine learning, in particular AI, is currently a form of alchemy. So he claimed that researchers do not know why some algorithms work and others don't, which architecture to choose, and so on. Yeah, so it's a lot of trial and error. We are now 5 years later, but still, I mean, if we train neural networks, it's a lot of trial and error, it's a lot of tweaking. So a profound theoretical mathematical foundation is still missing. Yeah, and then, I mean, if you go further, we see that there are a lot of warning signs, in particular now with ChatGPT these days. So for instance, Stephen Hawking said, well, I mean, it could lead to the end of the human race. I think we are very far from that. But as said, I mean, there are a lot of critical voices. And I mean, even more, there are also problems, in particular with reliability. So think, for instance, of problem with safety. There were already various incidents where robots caused dangerous situations, and a self-driving car is also a robot. There's problem with security. One can hack into these systems, for instance, in a hospital system which uses AI, make modifications which nobody realizes. Problems with privacy. All these methods need a lot of data, and sometimes these data are just collected in a, let's say, non-sensitive manner. And then last but not least, problems with what I want to call responsibility. These decisions are typically black box decisions and are also often biased. And so I think it's fair to say that one current major problem worldwide is the lack of reliability of AI technology. And then, I mean, if I look, for instance, around myself here in Germany and in the EU, there are some laws which are now being initiated to ensure reliability, and I'm sure that also happens in various other parts of the world. But what does it take to make AI really reliable? Well, I mean, from, I think, my perspective, and there are many others who think the same way, and I hope you also all agree, we need to derive a profound mathematical understanding, because only then, if we have, for instance, error bounds and so on, only then do we have really trustworthy approaches and can say these approaches are now reliable. Okay, so let's start with a mathematical perspective on reliability and AI, and I would like to take you a few years back in the beginning when everything started, because artificial intelligence is nothing new. It started with McCulloch and Pitts in 1943, and their idea is they wanted to introduce AI, and since we humans, at least we believe that we are intelligent, what he wanted to do is he wanted to mimic the functionality of the human brain. Now, the human brain consists of neurons which are interconnected, which you see here, and then there are electrical signals passing around. And so what he did was he mathematically modeled an artificial neuron and connected that to a neural network. And as I said here, I mean, also today, basically these deep neural networks are one main workhorse for artificial intelligence. It's also one reason why now these approaches became that popular. So just in a nutshell, how does it work? And then I will show you the general formula for neural networks. So only to understand why it's set up this way. So a neuron works as follows. Some signals come in here, so these dendrites, and they might be amplified. This is mimicked here by these signals x1, x2, x3, and so on, and then the weights which might amplify the incoming signals. Everything is collected here. The neuron needs to decide whether to fire or not, and the modeling, the mathematical modeling here is in such a way that now the sum of xi, wi is compared to a bias term which is fixed, and depending on whether it's greater than b or less or equal than b, the neuron fires or not. Now you see, I mean, this is extremely simplistic. We'll make it a bit more complicated in a moment, but then, I mean, these are connected to a large neural network, and what is then trained and modified are these weights and the bias terms. These are the three parameters of the neural network when we connect all these artificial neurons, which we then update during training. And also, since I said this is extremely simplistic, what people instead use here, you see this is basically the Heaviside function, is the so-called ReLU, the rectifiable linear unit, the max of 0 and x. So then applied here to the difference of the sum minus b. Okay, so this is now an artificial neuron, a bit more complicated written. You see here again the sum and the b, which we discussed, and then here the so-called activation function. This could be the Heaviside function, which we saw on the last slide, but typically it's the so-called ReLU, the max of 0 and x. And then these are connected to a neural network. So what you see here basically are these artificial neurons. You have here the input neurons. Everything passes from the left to the right. You see here, for instance, for this artificial neurons, the incoming signals and then the outgoing. And here you see 4 outgoing, but these are all the same. Yeah, they are just linked to different neurons. And if we now combine everything to what a neural network is, then we see it's basically a function from RD to some RNL. And you see here you have basically a combination of these affine terms and activation function, and in the general formula you see the same. So these are now affine linear terms. You see this here, the weight measures and the biases now combined for all these connections. And then in between always the activation function, which is applied component-wise. So this is a neural network, a very, very mathematical object. And so basically ready for us to explore. Okay, so what do we do with it? Let me just also one time just very briefly show you the workflow, and then from this we will see the main mathematical directions which one today also pursues. So typically we have a very complicated function or a distribution which we want to learn. Maybe it's defined on some lower dimensional structure, and maybe it's a classification function. So you see here f can map to 1, 2, 3, 4, 5 up to k. And so in the easiest case, and computer scientists like to separate cats from dogs, You can have images maybe of cats and images of dogs. And what you have at hand is not the complete function. So mapping each image of a cat to a, let's say 1, each image of a dog to the value 2. But we just have sample values. We have a couple of images and we know the function values. Yeah, so the labels. So here, for instance, 1 or 2. This data, which we have, we now split into 2 sets, a training and a test data set. The test data set we set aside. We only use the training. And now the task is to approximate the function f by a neural network. Remember, a neural network is just a function. And so now we need to choose, first of all, the architecture of the neural network. So how many of these layers do we take? How many neurons in each layer? Which activation function? Maybe we don't want to train a fully connected neural network, so we set some of these weight matrices, the entries, to 0 already at this point. Yeah, and this is also what this colleague Ali Hakimi in the beginning referred to, that this is a lot of trial and error still. Once we have that, we train the neural network. And remember, now we learn the weights and the biases. And I don't want to go too much into the details. It's trained by a classical algorithm. It's a variation of gradient descent, which I assume, I mean, many of you know, because gradient descent, this would require computing a gradient for each sample value. But since the samples are in the millions, we cannot do that. So the gradient is not computed for each sample value, but just for a random collection. We learn the weights and the biases. This gives us a neural network function. And now we see how this neural network function, how close it is to f. And the way we check that is now with the test data set. So now we ask, the neural network has now understood all of my training samples. It correctly classifies those. This is what I train to. And now I check how good it can transfer this to other types of data. So now I put in other, let's say, images of cats and dogs, and I check whether it correctly classifies those. So this is typically a workflow, how you apply this technique. So now I'm focusing on these deep neural networks. And so from this, several areas arise. Just the area of expressivity. I mean, this sounds catchy, but from a mathematical standpoint, this is just approximation. Yeah, so this asks the question how to set up the network architecture. And you saw, I mean, the question is how many neurons to take, and so on and so on. This leads into the areas of approximation theory, applied harmonic analysis, and so on. Then learning. What does the algorithm converge to good local minima? Although, I mean, the problem is highly non-convex. Now, this is still a mystery. And there's a lot of effort going into this using tools from optimization, optimal control, also areas like, for instance, algebraic differential geometry, to understand the energy landscape where we optimize over the geometry of the energy landscape. Generalization, or that is generalized so well to the test data set. And I mean, it's used a lot of learning theory, probability theory, statistics, and so on. Yeah, so expressivity is maybe the oldest area, and it's maybe the most explored. Generalization maybe the hardest in some sense in this direction. And but for reliability, this is absolutely crucial, because what we need are in particular error bounds for the overall success of neural networks. And so now I would like to start, I mean, showing you, let's say, some snapshots where I think reliability is key, or which are important for reliability, maybe where we are. I'll show you some examples. And then hopefully you get some maybe inspirations where also this field can go. So generalization, I think, is one key aspect. And so what we ask there typically is, why do neural networks perform that well in the high parameter regime? So what does it mean? I mean, what we see is that networks perform best if they are very large. So if you ask someone which network to take, they will often tell you, well, take the largest, which still fits in your GPU. And so that's why also companies like Google and so have such an advantage, because they can train these really huge neural networks with basically billions of parameters. And the effect you see here, that's a very classical picture. It's the so-called double descent curve. So let me walk you through that. So on the left-hand side, you see what we understand by statistical learning theory these days. This is here the size of the neural network, the capacity of the high processing class. This is the error. The training error, the larger the network, the more the training error goes down because you can fit the data better. But the test error after some point goes up again. And that's this phenomena of overfitting. The network, if it has too much flexibility, it can do some awkward things, and it could aim to encapsulate the let's say, the data too closely. And so this leads to problems, in particular, if we have some outliers. So this is very well understood, these curves, but what happens these days is what you see here on the right-hand side. And you realize the left-hand side here corresponds to this picture, but now we have here also the right-hand side. Yeah, so after some point, the test error again goes down. And so this is the very high parameter regime. And so the larger the network, the better. There are now many approaches aiming to understand why this happens this way. VC dimension, Rademacher complexity, neuroattention kernel, a very, very exciting area. Let me show you one example now, which takes us also to, I think, another very hot area in this regime, which are graph neural networks. It's a generalization of classical neural networks. Graph neural networks take as input graphs. So a graph, and each node now has a feature vector. So this maps these graph nodes to a feature vector, so in RC. And it's a generalization of classical neural networks because you can interpret, let's say, for instance, a matrix or a Euclidean vector as also a graph. And there's a lot of effort now studying graph neural networks. So this is where research these days also progresses with own conferences, because there are exciting applications, so recommender systems, fake news detection, this whole social media, and analyzing this. Also chemistry, for instance, molecules are graphs. So in this regime, you can actually ask a generalization question, which is a special type of the full generalization question, but this, for instance, we can answer completely. And so what you certainly expect for generalization, again, I mean, what I said before is you have graphs in your training data set, and you want that the trained neural network now generalizes from those known graphs to some which it has not seen before. Yeah, so let's assume you have this graph on the left and on the right hand side in your training data set. You trained your neural network on it, it classifies it correctly, and then the test data set now contains this graph, which you see here on the left-hand side. So the question is, how good does it generalize to this? And these two graphs look very much alike, as you see. So one can make precise what it means that two graphs model the same phenomena. And then you can ask now let's say, a subpart of the generalization question, because you can ask, if from these, let's say, graphs which model the same phenomena, I have one in my training data set, does the trained graph neural network generalize to the others in that same class? And then, I mean, the neural network which is trained should have the same repercussion on both graphs. So how do you define modeling the same phenomena? You can say, well, I mean, you have a continuous space. You see this here, basically, and these two graphs are a sampling of the same continuous space. Then they model the same phenomenon. There are also other approaches like graphone approaches, which are limit objects of graphs. And you can also modeling the same phenomena defined this way. There are various ways to make this mathematically precise. But then, I mean, for this type, I mean, what you can do is you can actually prove rigorous generalization error bounds. So basically, if you see here, what we could show is that the error which you make, if you define it this way, if you have one graph which is in the training data set and the other which models the same phenomena in the test data set, you can estimate this error by so-called graph Laplacian for this, which is like a self-adjoint operator, which models the geometry of the graph, the transferability of this, plus some consistency error, which is related to the density of the sampling from the continuous space. So you have a very precise bound. So in that sense, the sub-problem you can there solve completely if you use specific graph neural networks which use spectral filters. So this takes us in the world of applied harmonic analysis, for instance. So in that sense, I mean, this problem can be solved there, but in general, I mean, getting error bounds is one main problem. And also if you talk to practitioners, for instance, in various areas, electron tomography, telecommunication, and so on, because these error bounds are missing in some fields, it's actually not possible or not allowed even to use such methods at this point. And mathematics really has, let's say, a huge task there, but also a very exciting one. So another area which is now very different is the area of explainability. So these are all deal with, we have access to the training process and so on. But now let's assume I have a trained neural network, which someone gave to us, and we have to understand how it reaches decisions. So let's assume this AI-based approach decides that someone is not eligible for a position, for a job, and then this person asks why. What are the reasons for the decision? And so explainability aims to answer that question. And what I would also like to show you here and point out maybe is that you see, I mean, I wrote here these areas of mathematics which are involved, and what one observes is that basically the whole field of mathematics is needed to answer all those questions, which I think is very exciting. You also see that a lot of people from different areas of mathematics with their background now jump into this field. This is also certainly key for reliability, because we want to understand, if we have not access to the training process and have just access to the algorithm, how decisions are reached. So how does it work? Well, I mean, the general philosophy is you want to understand decisions of these black box predictors. Let's assume I have a neural network which classifies this as a 3. And now I would like to understand how it reached that decision. And so these explainability approaches then put often like a heat map, which you see here, on an image, which then says the following. Well, I mean, these red pixels are important for the decision for that network. And also here, but these blue play against it. And that makes a lot of sense, you see, because these openings here are important for deciding whether it's a 3 or an 8. So looking at these openings makes a lot of sense. So here the neural network really did something smart. But certainly one can ask, I mean, what does this coloring mean? So what exactly are these relevance scores which are now assigned to each pixel from a mathematical standpoint? When can I say a relevance map is optimal? What about other modalities? I mean, typically these algorithms just apply to images. And also, maybe not single pixels are important, but maybe a combination of pixels. And the ultimate goal is actually to be able to question and communicate with AI as a human about the reason for a decision. Maybe with ChatGPT, we can make now, let's say, a quantum leap towards that vision, but right now we are very far from that. But still, this is the goal. And one thing which, to my mind, is also often overlooked, the explainability approach itself needs also to be reliable. And I mean, people have nice approaches, they produce nice heat maps, but in fact, you can only rely on it if the approach itself is reliable. And so this needs, again, a mathematical underpinning. So let me show you one example in this direction, which comes from information theory. Information theory asks typically the question, I have a person, she has a message, and she transmits the message to another person, but she only can transmit part of the message. But then the other person should still be able to decode somehow the complete message. And the rate, how many, let's say, how many bits are sent, this is the rate, and how much the error is of reconstruction is the distortion. Now we can phrase this explainability approach in this framework. Let's assume the first person has the original image and the neural network. And the second person for decoding also has the same neural network. Now, the first person sends parts of this image, hopefully the relevant pixels, to the second person. He first needs to obfuscate the image to a complete image again, because otherwise he cannot put it in his neural network, and then he gets also a decision. And so this is the rate, is how many pixels to send. You want to have a concise, let's say, explanation, so very few of those relevant pixels. But then also the error should not be too small, too large. And the error here is the distance between these decisions. So if that's small, if this distortion is small, then those were really the relevant pixels for that decision. And so you can now define what's called a rate distortion function. We want to have very few pixels, but the distortion should be still small. But computing these pixels is very hard. You can imagine it's an optimization problem. You can prove formally that computing a minimizer is very hard. It's NPPP complete. So we can relax that. That's the traditional way of relaxing it. We now formulate it as such an optimization problem where here we don't just take some pixels or not, but we put a little L1 norm on it. A little L1 norm also promotes that we just have very few significant pixels, but it's now a way that we can use linear programming to solve it. So now every pixel will be also assigned a relevance score, but we aim for having a concise explanation. And also, since we now have a concrete optimization problem, we can perform a rigorous mathematical analysis as well. So let me show you some pictures. So here we have a neural network which classifies this as a dog. And you see here different explanations of different approaches. Here you see ours, and what you realize is that these are very concise explanations with very few pixels. And basically it says the neural network looked at the head of the dog to understand or lead or reach the decision that this is a dog. You can also use this to compare different approaches. You can compare how many pixels are taken versus the error. And then you see that ours here perform the best in this regime. That's also not that surprising because they are tuned towards it. But on the other hand, because you might now say, well, this is actually a really unfair comparison, let me say that the other approaches also typically use this measure, because what they do is they align the relevant pixels and then start flipping them from one side and then see, look, when the decision changes. Yeah, and so basically this is exactly the same. So in that sense, it is a measure which also a lot of other approaches take. I can say this is the end of the story, and you can, for instance, say why to take random pixels for obfuscating. Well, this might least distort the meaning, but I mean, it leads to very awkward images. So you can use what are called these generative adversarial networks to in paint to fill these images. So if I go back, yeah, so what you see here, to fill this in a better way. And the second is, we already said, why assign a relevance score to each pixels? Why not do something more high level? And so here you can think of, there are various representation systems for images. For instance, wavelets is a very classical system. It's also the basis for JPEG 2000 for the compression standard. So here are a couple of wavelets. So you can write every image as a linear combination of wavelets, which leads to very, let's say, a very efficient representation. And so now we can put relevance scores to the coefficients of these wavelet elements. And so the idea basically is now, so if you know about image compression, what you do is you have an image, input image, you compute the wavelet transform, you select the largest entries, you put the others to 0. That's also what is done in JPEG 2000. You reconstruct, and then you hope that the reconstruction is close to the original image. Now, what we do here with the explainability approach, we also have our neural network, we have the image, we compute the wavelet transform, we select the largest entries, we replace the unselected now with, for instance, random noise, and we reconstruct, and now we not compare the images, but we compare them through the lens of the neural network. Yeah? So here, each image we now put in the neural network, and then we compare the outputs. Yeah, so, but it's in the philosophy like image compression. And so what you can do, let me show you some examples. You see here, for instance, an example from telecommunication. These blue squares are buildings of a city map. The red dots are cell phone users, and the white blob here is the cell tower. And the neural network computes this black and white background, which indicates at each point how strong the signal there is. So you see here, for instance, the signal is really bad, and that makes sense because if you stand here, you have a lot of buildings which are between you and the cell tower. But this doesn't make any sense, yeah, because I mean, this cannot be an area of bad reception, because if you stand here, you stand basically right in front of the cell tower. So now you can ask, did the network do something wrong? And you can ask, how did it reach the decision to put there this black area? And this is the explanation which you can get. And in fact, I mean, these cell phone users have bad reception. And so what turned out later on was actually there was a building missing in the city map. So there was an error with the data. The neural network did something correct. And so this you can also find out by these explainability approaches and then correct for that. This is another example which shows you that you can also understand wrong decisions. So here in the first image, the network decided that this is a diaper, although it's obviously a dog with a man. And in the second image, it decided that this is a screw, although it's also a man now with a sweater. And now I will overlay the explanation to those images, and you will see why the network actually has come to that wrong decision. Yeah, so the explanation, so let me go back and forth. Yeah, so I will put it on top. And then in the first image, if you put that on top, what you see is by this wavelet type approach, the network has mistaken this because it has interpreted this as a baby. And then the diaper is not that far off. And here you can mistake this for a screw. So that way you can reveal why wrong decisions are taken and also correct for that. So what I would now also like to show you is two application areas. So we show now, I mean, how to basically deal with and understand neural networks and get a profound theoretical understanding of how neural networks work. I would also like to show you now how we can, to a certain extent, ensure reliability also in applications. There are two main application areas which are already mentioned in the beginning. The first are inverse problems, the second partial differential equations. And in the first, the questions we typically ask is how to combine deep learning and deep neural networks with classical approaches. And maybe a bit, let's say, more provocative, can neural networks and AI replace, let's say, specialized numerical algorithms at all in the future? I mean, to my mind, answer maybe that already, I think at present, I mean, let's say the physics-based approaches have valuable information, and you don't want the neural network to learn this twice. So combining that is the best way right now. But there are also a lot of approaches to actually learn physical laws right now with neural networks. And if this goes further, then maybe the second question you can also answer with a yes. So let me take you into the world of images for a moment and show you why neural networks are that effective and how we can actually use them in a reliable manner. So this area typically asks the following question. I have, let's say, a measurement operator, and which I would then like to invert. So I have here, for instance, my data, an image. I apply my operator to it. It can be an operator which puts noise on it. It can be an operator which takes measurements. It can be an operator like here, which takes parts of the image out. And then from the distorted image or from the measurements, I would like to reconstruct F. I would like to invert this operator, so it's an inverse problem. And the classical approach is here. I minimize this functional. This is the data fidelity term, and you see if you minimize this, you aim to solve this as accurately as possible. The second is usually a term where you have the chance to incorporate properties, additional properties of your solution. Yeah, because otherwise, I mean, for instance, here in this image, you have these missing parts. How do you actually fill it? You can fill it with white, you can fill it with anything you want. Now, so you need something to correct for that. You need something which ensures you that you get a realistic image afterwards. And so this is the task of this regularization term. Incorporating properties of the original image. Okay, good. So how do you, and so what I would like to show you then is, I mean, how you combine neural networks with such a classical approach. But let's first talk about a bit about this regularization term. We already got a bit familiar with wavelets. You can put wavelets here. You can also put an extension of wavelets here, which is a bit better suited to images because images are as you see, governed usually by edges, directional structures. Their wavefits are not the best you can choose. So what you could choose are elements which are themselves directional. Now, so these elements you get in every position, you get at every scale, and you get also in each direction. And so let me not write down the formula because it's quite complicated and involved, but this is the basic intuition, and you can show also theoretically that these lead to optimal compression rates for certain model classes of functions. And so there are also a lot of algorithms here, even also using neural networks. So if you want to try things out for this part of inverse problems, I mean, feel free to go there. You can download a lot of stuff and test some of the approaches. So now, let me go back just to show you. So here now we can take shearlets in this regime. Okay, so now, I mean, going into the area of medical imaging, which is one of the main areas for inverse problems, and looking at computed tomography, which is a very classical problem, and many people are working on solving it. So if you have already been used, or a CT scanner has already been used on you, you know, I mean, there's some rotation going on. So what it does is you have here the interior of the human body, you compute line integrals through it. This gives you a 1D function. This gives you then one slice of the sinogram, and then you rotate it. And so this fills the sinogram, you rotate by 180 degrees. And from these measurements, you want to reconstruct the interior of the human body. This is not difficult, but it becomes really hard if you don't have the complete data. There can be two reasons. One is that due to radiation, you don't want to expose the patient to too much. So you only sample for instance, every second or every third angle. But even worse, it could happen in certain cases, dental CT and so on, electron tomography, that you cannot do the 180 degrees. And then you not only have, let's say, every second angle missing, but you have a huge chunk of data missing. And that's much more difficult than this low dose CT. Yeah, so you have this whole area of data missing, which you don't have access to. And so now if you use classical algorithms, the algorithm I just showed you, so for instance, you have a 60-degree missing angle, and this is your original image. Even if you go to a sophisticated approach, like we discussed in the beginning, this sparse regularization with shearlets, which we had on the first slide, you make a lot of errors because you just have data which you cannot recover. And it's just basically impossible to design a mathematical model for the interior of the human body. Yeah, so that's a huge problem here. And the data is just too complex for precise mathematical modeling. And this is where deep learning is actually needed now. And there are now various approaches how to combine these two worlds. So there are what I might call supervised approaches. Maybe the easiest is to train a neural network end to end. You train it so that it, from, let's say, measurement data, reconstruct the original image. Now, if you have enough of these pairs, you can train your neural network, but basically you throw all physics overboard and let the neural network now learn all the physics, which is often a huge problem. And if you have that information, for instance, the measurement operator, why not include that? Now, or you incorporate information about this operator in the neural network. There are also other approaches where you break open algorithms and you insert the neural network in certain parts where, for instance, denoising is used. Then what I might call semi-supervised. So there, you basically take your reconstruction and you replace the regularization term by a neural network. There are approaches in this direction and so on. So there you don't use the neural network, let's say, for the full problem, but just for a part of the problem. And that makes then also, to a certain extent, semi-supervised. Or you could also say the output of neural networks, these are a good prior for natural images. There's this very interesting approach, deep image prior, and use it that way. I would like to show you now also one approach in a bit more detail. What you see here on this type is the neural network, which is usually used for inverse problems. So there's now a particular type, it's called UNIT, and you see how it works. You have some input here, the size of an image. It's first compressed and then extended again, because you need an image as an output, and then you have all these skip connections to transfer information which you might otherwise lose due to the compression in between. So it's like an autoencoder with skip connections. So I said, I would like to show you one approach which also ensures to a certain extent reliability. Now, from my perspective, I mean, what I would like to advocate, since neural networks per se and this end-to-end, I see very skeptical these days in sensitive areas, sensitive applications, because we don't have, let's say, all the mathematics we need. But what you can do is the following. You can use model-based methods as far as they go, and then complement with AI-based approaches, in particular neural networks, only where it's necessary. And you saw here what you are missing is basically this part where you are missing the data. So you can do the neural network or tune the neural network just to take care of this, and then combine both. Yeah, so then you have theoretical guarantees for the model-based method. You have more reliability because you know exactly what the neural network does. And also, since the neural network has not do everything, you get a better performance and it's less than a black box. So here, basically, what we did was we first solved it with sparse regularization using shillets. We then did another shillet transform, and which revealed what has been learned and what not, what has been recovered and what not, and then use the neural network only for those components, for those shillet coefficients which have not been recovered, and then combine those. And so now what you see, for instance, here is you have here the original image. This you already saw. These are the model-based approaches. Here you see a combination which does not do what I said before. It basically trains the neural network end-to-end, and it's already better. But now if you combine both worlds in the way I mentioned before, you get a significant better output. Yeah, so I think this is the message here. In a way, use neural networks, but use them smart, also in such a way that you increase reliability. And in the last few minutes, I would like to also, finish now with a word of caution, because there's something which is typically not discussed, and these are limitations. Everybody talks about neural networks, AI, it can do everything, but these methods also have certain limitations. And I think this is something which one also needs to be open about, and which one also needs to explore from a mathematical standpoint. Yeah, so they are not a Swiss Army knife, as one says, and there are problems, there are uncertainties, for instance, also algorithmic limitations. What I would like to just very briefly now touch upon is what can be computed on digital hardware, because we train our neural networks on digital hardware, and that breaks everything down to zeros and ones. And so this might cause some problems because the hardware itself is restricted. Now, what does it matter? Well, what we aim for is computability. That's one actually also area in computer science. So what we need there is, or what we ask for, is that the input-output relation can be computed on a digital machine for any given accuracy. Because then, if we have computability and we have theoretical error bounds, we know exactly what happens and we have a reliable output. If the problem is not computable, that is a huge problem, because our error bounds, our theoretical error bounds might not hold, or we cannot even check it because it's not, we cannot compute it. And it could be that we make always a constant large error, which we are not aware of. So we don't have guarantees for correctness. And the classical model for a digital machine is a Turing machine. So you see a Turing machine here. It's basically, it looks extremely simple. We have a tape, and then you have this head which moves around and does some computations. But it is believed that whatever you can do on a computer or on a laptop, for instance, in front of you, you can do on a Turing machine and vice versa. So it's considered that the mathematical model for computation. But you see also the problem, a Turing machine seems to be very tuned towards discrete problems. But in scientific computing, we typically have continuous problems. And so the question is, what effect does it have? And what we saw and what we found out was actually a solution of finite dimensional inverse problems. We just talked about inverse problems, is in fact not Turing computable and not even Banach-Mazur computable, which is a bit stronger by a neural network. Yeah, so that doesn't mean all of this is wrong, or it is that, but it means that it's not universal. There are many or some finite dimensional inverse problems where you don't have these guarantees, and it's to a certain extent related to the condition number, but not entirely. So there are also problems with computability when the condition number is okay. So what does it mean? Well, I mean, it's a problem because typically, as you know, I mean, we always use digital hardware, CPUs, GPUs in particular. And so we cannot construct algorithms which on digital hardware gives us the solution with any given accuracy. It could also be could point towards why instabilities, non-robustness actually occurs for deep neural networks. So this is a fundamental problem revealed by mathematics. But in fact, also mathematics to a certain extent gives us a way out, because what one can also show is that the solution becomes computable if you go to the analog world. There's an analog, let's say, equivalent to the Turing machine, which is the Bloom-Schupf-Smale machine, and there you can show things become suddenly computable. So maybe what one needs to do is to incorporate novel hardware, maybe complementing this in an optimal way with the classical digital hardware, and there are very exciting directions. You might have heard of neuromorphic chips. So these are chips which are considered to a certain extent analog computing. They are much closer model to the human brain as classical digital hardware. There's biocomputing, where you compute in biological cells, basically. And then also quantum computing. And let me say at this point, I mean, quantum computing, I mean here, not the qubits, I mean the true quantum computing, because if you use these qubits, you might have heard of, everything is again broken down to the digital world. So now if you look, and we checked also different other problems, I mean, there are many instances where things are not computable, some classification problems, some optimization problems, a pseudo-inverse, also in the PDE world, there occurs certain problems if you view it from that perspective, from a computability viewpoint. And so it could be that if you want to go to truly reliable AI from a mathematical standpoint, you need to go to other hardware platforms, neuromorphic computing, maybe quantum computing. And so let me conclude. From my perspective, AI has really impressive performance, but we still have a major problem with reliability. That makes it really exciting for mathematics. There are various instances where you can ask mathematical questions. We discussed generalization, explainability in a bit more depth, and also inverse problems, how you ensure reliability there. We also then in the end discussed limitations, which, as I said, I think it's something which also needs to be discussed and highlighted a bit more. And so maybe we need to go also to a different hardware world to, in fact, then get truly reliable AI. And so let me, I mean, in the last maybe 1 minute, just also mention, since we talked about reliable AI now for a long time, let me mention just briefly that we now have actually in Munich, specifically for that area, a new graduate school with a master program as well. And you see here, mathematical algorithmic foundations are one main point. It's set up between both universities in Munich, the TU Munich and the LMU. So if, I don't know, if you know someone who's interested, I mean, we have frequent calls and we are currently building up that school. And as said, mathematics and these theoretical foundations are also one major part in there. And let me conclude here, and thank you so much for your attention.